Marcus, we still have participants entering the platform. So if it's okay for you, we can give maybe a minute more.
Sure, perfect.
Thank you. Okay, I think we can start the webinar. Thank you.
Okay. Yeah, so I would like to welcome everyone to the second webinar of the WCRP Explaining and Predicting Earth System Change Lighthouse Activity webinar series. My name is Marcus Donat. I'm from the Barcelona Supercomputing Center, and I'll be again one of the moderators of today's event. The webinar is part of the WCRP Lighthouse Activity on explaining and predicting Earth system change. And if you want to know more details about this activity, follow the link that is posted in the chat now. Just briefly, the overarching goal of the Lighthouse activity is to take major steps towards the delivery of an integrated capability for quantitative observation, explanation, early warning, and prediction of Earth system change on global and regional scales, with a focus on the annual to decadal timescales. And this Lighthouse activity is organized in three themes, which deal with the monitoring and modeling of Earth system change, the development of an integrated attribution, prediction, and projection, and the assessment of current and future hazards. Just briefly before we start, also a reminder again about the WCRP Open Science Conference that will take place in Kigali, in Rwanda next year in October, and where these and the wide range of other topics will be explored in detail. And for more details and to register your interest, also follow this link that's indicated here and maybe also put in the chat right now. And I will now pass on to our other moderator of today, Lijing Cheng. Lijing.
Hello, thanks Marcus, and a very warm welcome from my side. I'm Lijing Cheng from Institute of Atmospheric Physics, Chinese Academy of Sciences. Before I introduce our first speaker, I will provide an overview of today's events and the modes for interactions. The other three speakers will present before the QA section. However, during their talks, feel free to post questions and indicate to whom your question is directed to using the QA feature at the bottom of the Zoom window. And everyone can unvote the questions posted there. Please reserve the chat function for technical issues related to the webinar and use the QA for the questions to the presenters. We will then get to these questions in a discussion session following the presentations. We also have a number of experts in the audience, so we want to encourage a lot of interactions. So for presenters, we are going to give you a warning when 5 minutes are left and when 1 minute is left for you to wrap up. So now it's my pleasure to introduce our first speaker, Dr. Michael McFadden. Michael is a senior scientist at NOVA's Pacific Marine Environmental Laboratory in Seattle, Washington. His research focuses on large-scale tropical ocean dynamics, ocean atmospheric interactions, and the ocean's role in climate. He received a PhD in physical oceanography from the Scripps Institute of Oceanography in 1980. For the past 40 years, he has been involved in developing ocean observation systems for the climate research and has been involved in and also forecasting. So Michael has published over 300 articles in the peer-reviewed scientific journals, and is one of the most highly cited authors on the topics of El Nino. And also he is a past president of the AGU and has received several medals and prizes in recognition of his work. So thank you, Michael, for being here, and the floor is yours. Can you share the screen and start? Thanks.
Yes, thank you, Li Jing. And let's see if we can. Okay, can you see my screen?
Yes.
Yes, Mike.
Okay. And we're in presentation mode now?
Yeah, all works well.
Yes.
Thank you.
Okay, well, thank you, Li Jing, for the introduction. Thank you, WCRP, for the invitation to speak today, and welcome to you all. Good morning, afternoon, or evening, wherever you may be. In this short presentation, I'm going to talk about the causes and the consequences of this extended period of cold conditions that we've experienced in the tropical Pacific over the past couple of years. And just as a brief background, El Nino and the Southern Oscillation, or ENSO, this is the strongest year-to-year fluctuation of the climate system on the planet. It originates in the tropical Pacific through interactions between the ocean and the atmosphere, mediated by wind and sea surface temperature feedbacks. We refer to the warm phase of ENSO as El Nino and the cold phase as La Niña. This is a problem that has commanded the attention of the scientific community for well over 50 years because it's such a fascinating scientific problem. And it's motivated largely by the fact that ENSO has impacts on patterns of global patterns of weather variability, as illustrated in the center panels here, and has effects on human and natural systems, profound effects on human and natural systems. And so you can see the typical El Nino and La Nina impacts in December through February. This is the boreal winter, the peak season of ENSO development typically. And these patterns represent shifts in the probability for certain types of patterns to occur, like drought, floods, heat waves, or extreme events, for example, effects on tropical storms. We are now experiencing a extended period of La Nina conditions, and this just shows the latest patterns in the tropical Pacific for October 2022, last month. You can see in the upper left here is this cold swath of sea surface temperature anomalies, 1 to 2 degrees Celsius below normal from the coast of South America out past the international dateline. That's accompanied by stronger than normal easterly winds. The trade winds have intensified along the equator, stronger than normal westerlies at the upper levels of the troposphere. And this is a signature of the intensified Walker circulation that typically accompanies La Nina events. And associated with that are shifts in tropical rainfall. Normally, we have heavy rains over the warm pool of the Western Pacific. Those have shifted westward over Indonesia and the Philippines. And it's dry now in this worm pool region. Also dry north of the equator, normal position of the ITCZ, which is indicating it's shifted northward, and dry in the normal position of the South Pacific convergence zone, indicating it has shifted southward. Now, this is just the most current month, but for the past 2 years, we've had this pattern in place, and it's produced significant impacts on weather around the world. And these are all what we might expect to see during a La Nina event. Extraordinary rains in Australia, Indonesia, and in the Philippines, an extraordinarily wet summer monsoon season in South Asia, particularly the floods in Pakistan were supercharged by global warming, but La Nina also had a major impact on this. In the southern tier of the United States, we've been in drought for 2 years, and one of the biggest reservoirs in the United States, Lake Mead, is drying up. And where I live in the Pacific Northwest, we had a very cold and rainy winter and spring last year. So these are some of the extremes that we've been experiencing over the past 2 years. We have various indices to characterize the ENSO cycle, and this is one of the more commonly used, the Niña 3.4. It correlates well with global impacts. It's a large areal index of deviations from normal in the central and eastern Pacific, where the overlying atmosphere is particularly sensitive to changes in sea surface temperature. This is a 40-year record of Niña 3.4, goes back to 1980, and it ends in October of 2022, last month. The red peaks are the El Niños and the blue troughs, La Niñas. You can see the big El Niños of the past 40 years, 82, 83, 97, 98, and most recently 2015, 16. And then you can see these La Niñas. And here we are at the end of the record. We have a 2-year double dip La Niña in progress. Now, an important characteristic of the ENSO cycle is what we call ENSO asymmetry. And you can see it by eye here that typically as a group, El Niños tend to be stronger, but La Niñas tend to last longer. And this is because of fundamental nonlinearities in the climate system that produce this asymmetry. One of the characteristics of La Niñas lasting longer is they often occur in successive years. For example, as we're seeing now, but you can look in the record and see about 50% or more of La Niñas are 2 years, or in some cases, in this 98 to 2001, this was a 3-year La Niña. So I want to compare the most recent event to La Niñas of the past. And what we're going to do is we're going to chop this record up into 3.5-year segments. And we're going to start the year before the first La Niña minimum, and we'll go to 2 years after. And so we're going to center these segments of the Niña 3.4 time series around La Niñas of the past 60 years. We're going to go back to 1950s to the 1950s. So these are 11 La Niña events, and here we're starting July, the year before the first peak, and we're going to January, 2 years after the first peak. And this is kind of a messy plot, so we're going to clean it up a little bit, and we're just going to look at 2 curves. One is the average of all those events, that's the thick black curve, and one, the blue curve, is the current situation. So here we start in, let's look at just the thick black curve. So starting the year before, July the year before the first La Niña, we see we have typically a moderate strength El Nino. And then the system transitions to the first minimum at the end of year 0. And then it tends to revert towards normal, but then it comes back to a second dip. Now the second dip tends to be weaker than the first, and the spread around it is larger because not all La Niñas are 2-year La Niñas, and so there's a wider spread. And then by the 3rd year, typically things return to normal with an even larger spread. Now let's look at what happens in this current event. We start out in 2019. It is an El Nino, but it's a borderline El Nino. It barely makes the definition of El Nino at 0.5 degrees Celsius above normal for 5 months or so. It does transition to La Niña, and the first peak in late 2020 was close to the average of these 11 previous La Niñas. There is a second dip here. And interestingly, instead of reverting towards normal in the 3rd year, this current situation is hovering around -1 degree Celsius colder than normal. So it's a very unusual event. Now, the kind of conventional wisdom for why we get multi-year La Niñas is that the stronger the preceding El Nino, the more likely it is that we'll have a double dip La Niña. And let's look at this hypothesis in a little bit more detail. I'm going to superimpose 3 more lines on this plot. And these are for the 3 big El Ninos of the past 40 years, 97, 98, 82, 83, 97, 98, and 2015, 16. And you can see that each of these big El Ninos were followed by double dip La Niñas. And in fact, 97, 98 was followed by a triple dip, 1, 2, 3. And so this raises two questions. The first is if the first question is, why is it that the amplitude of the preceding El Nino determines whether or not we'll get a multi-year La Nina? That's the first question. And the second question is, if that hypothesis is correct, why is it that we have such a extended period of cold conditions, likely to be a triple dip for such a week preceding El Nino? And so let's look at this issue in the context of Fei-Fei Jin's recharge oscillator theory, a main premise of which is that upper ocean heat content is a predictor for ENSO variability. And I want to go through three key attributes of this theory using these two time series. One is the Niña 3.4, you've seen this before, and the other one is a measure of upper ocean heat content, which is basically the average of temperature anomalies in the upper 300 meters from the coast of South America to the coast of New Guinea between 5 north and 5 south. And so first key attribute of this theory is that a buildup of excess heat content along the equator is a necessary precondition for El Nino to occur. And you can see that in these time series, that the red curve, the heat content, is leading the blue curve, SST, Niña 3.4 SST, by about 1 to 3 seasons, depending on which event you look at. The second important attribute is that El Nino purges excess heat to higher latitudes, which terminates the event. And let's look at 97, 98. You can see that as the sea surface temperatures are approaching their peak, there's a rapid discharge of heat from the equatorial band, leaving a very large deficit. And this cold, extreme deficit of heat content puts in place the conditions for the follow-on La Nina event. And the third important attribute is that the time between El Ninos is determined by the time it takes the equatorial band to recharge. Now, in this particular case, 97, 98, there was such a huge deficit, it took 3 years to recharge the ocean, the equatorial band with enough heat to trigger another El Nino in 2002, 2003. But in the meantime, there were 3 successive years of La Nina. So that seems to work throughout much of this record, but then what happens at the end? Not only was the preceding El Nino very weak, but it didn't purge any heat from the equatorial band. The heat content has stayed high in the equatorial band despite these cold temperatures. And so clearly, recharge oscillator theory is not providing a framework in which to interpret this most recent event. So what could be happening? And here, I want to propose one hypothesis, and this is, we published a paper on this in September in the Frontiers of Climate. And what we're arguing is that events external to the Pacific Ocean triggered and sustained this event, in particular, a strong Indian Ocean dipole in 2019 and an Atlantic warm event in 2021. And these external forcing from other tropical ocean basins are mediated by changes in the Walker circulation. And as background to this, let me just show you 2 papers written about 10 years ago. This is one from Takeshi Izumo et al., in which they note that the Indian Ocean dipole actually can be an effective predictor of following El Nino or La Nina. And it's a quote from the paper here: a negative phase of the Indian Ocean dipole is a predictor of El Nino 14 months before its peak. And similarly, a positive phase of the Indian Ocean dipole often precedes La Nina through modulating the strength of the Walker circulation. So file that one away for a moment, and let's look at another paper written about the same time, 2009. Are Atlantic Niños enhancing Pacific ENSO events in recent decades? Now, if you put a question in the title of your paper, you know what the answer is going to be, and the answer is, of course, yes. And what these authors note is that when you have an Atlantic Niño, this is in the boreal summer season, these are most often developed, you have rising air mass over the Atlantic Ocean, it alters the Walker circulation, so you have sinking over the eastern and central Pacific, and then a divergence of winds at the surface, creating stronger than normal trades. This initiates the Bjerknes feedback. And even as the Atlantic Niño fades away, they only last a season in the boreal summer. The Bjerknes feedback amplifies in the Pacific and you can get a La Nina. Well, let's look at what happened in 2019 through 2021. The first thing to note is that we had a record strength Indian Ocean dipole in the Indian Ocean, with cold in the east and warm in the western Indian Ocean basin. And Indian Ocean dipoles terminate in a phased sort of way. The warm anomalies in the western Indian Ocean persist while through wind evaporation SST feedbacks, but in the eastern Indian Ocean, it warms up. And so you reach a point in the boreal spring following an IOD where the entire Indian Ocean is warm. It's 5 minutes, you said?
Yes.
Yes, okay. Okay, so you reach a point where the entire Indian Ocean is warm. This is called the Indian Ocean basin mode. And this triggers enhanced convection in the eastern Indian Ocean, which is fed by enhanced trade winds in the Western Pacific, and this leads to the development of a La Nina condition. And then in the boreal summer of 2021, we had a moderate Atlantic Niño develop, and according to the paper I mentioned on the previous slide, we have ascending air masses over the Atlantic Ocean, descending over the Pacific, the strengthening of the trade winds in the Pacific, and the development of a La Nina condition in 2021. So this is a summary of these mechanisms. It looks complicated, but it actually is quite simple. The bottom panel here shows what typically we think happens. Big El Nino discharges heat from the equatorial band. You get a negative heat content, and this, if it's a large enough negative heat content, you can get not only a first-year cooling, but a second-year cooling. That clearly did not happen in 2020 and 2019 and 2020. What we think is this record strength Indian Ocean dipole yielding to an Indian Ocean basin mode in the boreal spring of 2020 led to intensified easterlies, and then we had a continuation of cold conditions through the development of an Atlantic Niño in 2021. Now, let's go back to this plot. So we have an explanation, or at least a hypothesis, for why we have a double dip La Nina, but this event looks like, from the observations, it's going to last the third year. What do the forecasts tell us about this? And I know others will talk about forecasts, but I just want to briefly touch on this here. This is the forecast plume constructed by the International Research Institute for Climate and Society. About 20 groups worldwide routinely issue ENSO forecasts. This is a forecast for Niño 3.4 from October 2022 initial conditions. And here we are stepping forward in time. And you can see virtually all of these forecast models are telling us that these cold conditions will continue through the boreal winter of 2023 and probably fade away in the boreal spring of 2023. So here's NCEP's assessment of the situation. 76% chance of La Nina during Northern Hemisphere winter, with a transition to neutral conditions by February, April of 2023. This is about a week old now, 2 weeks old. Okay, and so what this means then, if you look at the precipitation forecast for the globe in the coming season, you see the typical La Nina fingerprint. Higher probability than normal for heavy rains in Australia, Indonesia, and the Philippines, drought conditions in East Africa, wet South Africa, continuation of drought in the southern tier of the United States, wet in the northwest of the United States, and so on. So the extremes that we have seen over the past 2 years associated with this extended La Nina are likely to continue at least through the next several months. That's the message here. So let me conclude then. The 2022 La Nina has had major impacts on the climate system around the globe the past 2 years. Conventional recharge oscillator dynamics fails to explain the onset and persistence of this event. And we're suggesting interbasin interactions may account for the development of this La Nina, given the record strength Indian Ocean dipole in 2019 and followed by an Atlantic Niño in 2021. And then finally, the forecast models and observations indicate that this will become a triple dip La Nina. These are, they're not unprecedented. They've happened before, but this will be the first one of the 21st century. And they are rare. And this particular case where there was no strong preceding El Nino challenges, again, our understanding of this phenomena we call ENSO. And so I think there's going to be a lot of research done on trying to understand exactly what has happened. And I think we'll be seeing more papers coming out about potential mechanisms for the onset and persistence of this cold condition in the tropical Pacific for 3 years. With that, I'll conclude and thank you.
Thanks, Michael. It's really nice presentation, and any questions will be addressed in the Q&A session. There are already 2 questions in the Q&A. Mike, you can take a look. Now, Marcus.
Okay, yeah, thanks, Michael, for this great opening. Now, it's my pleasure to introduce our second speaker, Dr. Fei Zheng. Fei received bachelor and master's degrees from Langzhou University in China and his PhD degree from the Institute of Atmospheric Physics at the Chinese Academy of Sciences in 2007. His current research interests include air-sea interactions, short-term climate prediction, and data assimilation. Since 2016, he has been a full professor with the International Center for Climate and Environmental Science in Beijing, China. And from 2010 to 2012, as a visiting professor, he visited the University of Maryland in the US and the University of Bergen in Norway. He is currently the Deputy Director of the International Center for Climate and Environment Science. He won the award of 100 Outstanding Doctors of China in 2009, and he was selected in the National Program for Support of Top-Notch Young Professionals in 2013 and supported by the National High-Level Talent Special Support Program in 2019. Fei, welcome.
Okay.
And the floor is yours.
Thank you, Marcus. I will share my screen now. Can you hear me and see my slides?
Yes, we can hear you and see your slides.
Okay, thank you. Thanks for your introduction. And hello, everyone. It is my pleasure to introduce our recent works, have such an opportunity to summarize our recent works on understanding the onset and the development of the double year or triple years La Nina events and its predictions in the last 3 years. I'm Fei Zheng from the Institute of Atmospheric Physics, Chinese Academy of Science. This is the outline. Firstly, I will briefly review the research and the prediction status of multi-year La Nina event. And then I will use the 2011 La Nina event as a case to describe the mechanism of breakout of a second-year La Nina. Through this description, can we find some useful information for the predictions? I will further introduce the necessary information we demonstrated for La Nina predictions before the summary. For the evolution of the La Nina event, Dr. McFadden has already pointed out La Nina events looks like have a tail and it easily persists longer than 1 year, especially after 2000. Five of the six first-year La Nina events continued more than 1 year and forming a second-year event. And for the prediction of the second-year La Nina event and showing by the performance of each models, for the last 4 second-year events, we can find that some area models were not able to predict this kind of La Nina event started from spring season. This also means, besides of the decadal variability of ENSO itself and the poor scale of the predicting the CPR Niños, the low prediction skills of the second-year La Nina event is another main reason for the decline of the ENSO prediction skills after 2000. We summarize the previous research from the case studies and diagnostic analysis and the numerical experiment and seasonal predictions to explore the onset and evolution of the multi-year La Nina events. Most of them, as shown by the diagram from John's paper, demonstrated the off-equatorial effects, especially for the off-equatorial subsurface effects. Now, based on a second-year case, the 2011 La Nina case, I will describe a clear process of the onset and evolution of it to show the key process for the onset of multi-year La Nina event. This figure shows the inter-annual analysis of the 5 variables varying along the equator in 2011, and the development of this La Nina event is quite clear at the equator. For the SIT anomalies, there are a shift of the cold, warm, cold conditions over the equatorial central to eastern Pacific during the whole year. A second cooling at the sea surface occurred in after the mid to late 2011, following the first cooling started from the fall of 2010. Corresponding to the characteristics of the SIT anomalies, anomalous at sea level and the thermocline depths shows a similar variation pattern. Meanwhile, the combined easterly and southerly wind anomalies demonstrate the dominance of the anomalous southeasterly wind over the whole equatorial Pacific region. Moreover, from the February to May, the positive oceanic heat anomalies in the equatorial Western Pacific excited a downwelling Kelvin wave associated with the eastward propagating Kelvin wave. A pronounced warming process existed in the equatorial Pacific during early to middle 2011. But after this Kelvin wave successfully reached the east boundary of the tropical Pacific, the warming process did not continue afterward and was replaced by a cooling process in the whole equatorial region. We can skip the evolution of special SIT anomalies, just focus on the cold SIT persisted over the off-equatorial region during the first year decaying phase, which was mostly pronounced in the tropical South Pacific. Obviously, the temperature anomalies at the thermocline depths can reflect the evolution of the second cooling event better than the SIT, because for the subsurface current field, a pathway can be found originating from the tropical South Pacific, and the cold water carried by the southeastern current was eventually transported to the equator, and which interrupted the eastern propagation of the warm water along the equator, and the cold water finally seemed totally occupied the tropical eastern Pacific again during this year. Consistent with the negative SIT anomalies, especially over the tropic South Pacific, which generates SLP center over the tropical South Pacific. The grading of the SLP acted to produce the cross-equatorial southern wind. The southeasterly wind can cause a stratification variation of thermocline to further spread the cold subsurface water to the equator from the off-equatorial region. From the vertical distribution of interannual temperature anomalies in the upper oceans, a striking feature is evident from the form of the cold water mass unpredictably appeared and persisting at the thermocline over this region, especially in May. And the range of this cold water mass gradually expanded and eventually reoccupied the whole equatorial center to eastern Pacific and in the following months. Based on these analysis results, we can find that the inclusion of cold water into the equatorial region took place at the thermocline, and the inclusion process was the key mechanism preventing the development of a warm event and causing a second year cooling during this year. But it's still difficult to distinguish whether the source of the cold water was from the south or from the north, as well as what kind of physical process was able to trigger the inclusion of the cold water. No, this figure shows that the cold subsurface water, which located in the tropic South Pacific, started to spread northward and broke into the equatorial region, successfully break the instant propagation of warm water along the equator in May and afterward. And in May, the inclusion of the cold subsurface water from the tropical South Pacific into the equatorial region are further strengthened. Along this arrow, it's clearly to see that the negative temperature anomalies during this inclusion process almost breaking into the equatorial region along the thermocline. And in May, the cold water in the tropical South Pacific started to break into the equatorial region along the thermocline and through the horizontal advection. And because the interannual variations of the upper ocean over the tropical Pacific are controlled by the surface wind, potential trigger for this inclusion process of a subsurface cold water can be found in enhanced southern meridional wind throughout the early to middle of this year. And the southeasterly wind reappeared over the tropical South Pacific around March and spread to almost entire tropical South Pacific from April. Finally, we can conclude that the onset and the development of this event is a surface LC interaction that drives the inclusion of subsurface cold water. We can summarize that during the first year decay phase, when El Niño tends to develop, but the cold water persists in the south of the equator from surface to subsurface. And the surface cold water acts to strengthen a southern meridional wind and bring the subsurface water invaded into the equatorial region along the thermocline and prevents the propagation of the warm water along the equator. Finally, the cold condition reappears in the center to eastern basin and develops to a second year cooling. In 2021, we met a similar situation from the onset of second year La Niña, and the southeasterly wind can be found, and that triggered the invasion of cold water from off equatorial region and then prevents the propagation of warm water along the equator from west to east. But the timing is slightly late than 2011. It's around from June to July. How about this year? In March of this year, although the LC interaction, LC states are displayed as a La Niña decay process, but we have already found that the cold water has invaded into the equator much earlier than previous events. As the persistence southeasterly wind over the tropical Pacific, thus after that, the spring season in this year, we can see a clearly invasion of the off equatorial subsurface cold water. And in this year, the tropical Pacific is mostly like on a developing stage of a new La Niña event, not a decaying phase. From these cases, we found an important feature is that the southeasterly wind triggers that off equatorial to equatorial subsurface invasion process. And this feature is a common result for all multi-year La Niña events we still need to further explore. We compared the difference in the developing phase of the first year and the second year La Niña event, and found an interesting thing is that the zonal wind stress is stronger in the second year. It's generally stronger than that in the first year, but the SLT and the SLP are generally weaker along the equator. To explain the inconsistency shown by the observations, we adopted the bijection feedback to make further research because it's a dominant mechanism on controlling the developing phase of the ENSO. And we separated this LC coupling process into 3 sub-processes to get more details, in which in which the zonal ST grading first leads to a zonal grading in total diabatic heating, which can be represented by the precipitation. And the zonal grading of the diabatic heating results in the zonal SLP grading, and then the zonal pressure grading drives the zonal wind stress. The BF intensity can be represented by the regression of the zonal wind stress with the zonal SLT grading. And the second year is obviously stronger than the first year, showing a quite confused phenomena of a weak SLT associated with a strong LC coupling stress. And this inconsistent is mainly from the subsurface 3. Well, the other two sub processes have no significant differences between the first year and the second year. And this difference in the sub process 3 indicates a slight weak LSLP grading could trigger a strong easterly wind over the tropical Pacific. Is this result bringing out our traditional understanding of Beijing feedback? The answer is definitely no, because when we use all months to calculate the relationship between the zonal SLP grading and the zonal wind over the tropical Pacific, the previous inconsistency in these figures are disappeared, indicating that the second year they had additional easterly wind from the off-equatorial region. And its source are from the tropical South Pacific before several months, consistent with our previous analysis results. And after showing these results, the following question is whether the southeast wind is useful for the realistic ENSO prediction. We all know that the spring predicted barrier for ENSO. Actually, our recent work also demonstrated that the ILC states in spring are actually closely related to the ENSO in winter. The coefficient is above 0.9, and especially after 2000, the zonal wind over the Western Pacific and the cross equatorial wind, and it means the meridional wind, it has over the Eastern Pacific are getting more critical for the following ENSO evolution. And we use this relationship, we can successfully predict the development of last La Nina event, the first year and the second year of this triple La Nina event, and use the LC information in spring. And in this year, and how about this year? We also wanted to we also want a coming third year La Nina event by AS reporter which is published in June, and we examine the status of LC field over the tropical Pacific in March. We can see that while the small client, these two variables shows the small client variables are nearly to zero and about close to the net average, but the southeasterly wind is the strongest since 1980, which are favorable for the emergence of the third year La Nina event, and both of the anomalous easterly and the southerly wind stress component are all important and each contribute 50% of the third year La Nina growth for the following growth respectively. Okay, we reached the summary. We can conclude that from the previous studies, we conclude that an important process, which is the surface LC interaction that can drive the inclusion of the off-equatorial subsurface cold water into the equator. And also after 2000, the contribution of the spring surface wind field over the tropical Pacific, its contribution to the following evolution of ENSO is significantly enhanced. I think this can help us to improve the predicting skills across the spring season. And the leading signal of the southeast wind can be regarded as a source to judge and also predict the triple year La Nina event. However, there are still many works need to do, such as how the importance of southeast wind and its triggering mechanism can be well or better reflected by the complexity models. And also, is there any obvious indicator shift for this process, for this inclusion process of cold water? Okay, that's all. Thank you for listening.
Thanks, Fei. Thank you, Fei. As before, if anyone has questions for Fei, please post them in the Q&A box, and we will address them during the discussion session. And now it's my pleasure to introduce an early career scientist, Xian Wu. Xian is an advanced study program postdoc fellow at UNCAR. She received her PhD from the University of Texas at Austin in 2020. Her research interests include climate variability and change, climate predictability, and ocean atmospheric interaction. And she used climate model simulations and initialized the forecast to understand the physical processes governing the predictability and the prediction scale of natural climate modes, including ENSO and the PDV. And Xian, the floor is yours. Can you share the screen and start? Thanks.
Thanks, Li Jing, for the nice introduction. I share my screen. Can you see the full screen of my talk?
Yes.
Thanks. My talk will be focusing on the predictions of La Nina, duration of La Nina events using the CESM multi-year forecast systems. Most of the work shown in this talk was done during my PhD at UT Austin, working with my advisor, Yoko Okumura, and collaborators, Pedro Dinazio, Clara Deser, and Steve Yeager. In this talk, I will first discuss the factors and mechanisms controlling the duration of La Nina events. And then I will show the predictability of La Nina duration using the 2-year CESM1 predictions. These results have been published in Journal of Climate, in which we also looked into the duration of El Nino events. In a later part of my talk, I will show some preliminary analysis of triple La Nina events. Here I'm showing you the monthly Niña 3.4 index since 1900 based on head-eye SST. This time series shows that individual El Nino and La Nina, their temporal evolution varies from event to event. We find that about 1/3 of the El Nino events and half of the La Nina events lasted 2 years or longer since 1900. And we also identified 6 triple-year La Nina since 1900, including potentially the current one. To identify the precursors of La Nina duration, here I'm classifying all La Nina events into those lasted only 1 year and those lasted 2 years or longer. This is based on the observations. Individual events are shown in the gray curve, and the blue curves are the composite mean of each type. And here we define the La Nina events when the Niña 3.4 index is below minus 0.75 standard deviation in any month during October to February in the first year. And 2-year La Nina are defined when the Niña 3.4 index remains below minus 0.5 standard deviation in the second winter. The right panel compares their composite mean evolutions, and we find that 2-year La Nina tends to be preceded by stronger previous El Nino and have larger peak amplitude than 1-year La Nina. Similar analysis are repeated with the 1800-year pre-industrial control simulation of CESM1. CESM1 show very similar results as in observations, including the ratio of 2-year to 1-year La Nina events, and also the leading factors. But the significance is more robust as we have way more samples in the long control simulation than the observational record. Then we would like to understand what are the mechanisms underlying these factors in affecting the duration of La Nina. First, I'm showing you the oceanic processes. This is the longitude time sections of the thermocline depth anomalies in color shading and SST anomalies in black contours, averaged along the equatorial Pacific for the 1-year and 2-year La Nina events in the CESM1 control simulation. The time is going up. We can see 2-year La Nina events tend to be preceded by stronger preceding El Nino, which triggers larger initial thermocline shoaling, which requires more time for the La Nina events to recover to a neutral state. And there are also other recent studies looking into the role of strong preceding El Nino in causing the multi-year La Nina and the discharge processes. Besides the oceanic mechanisms, we also find that the interbasin atmospheric adjustments also play an important role in affecting the duration of La Nina events. Here, I'm showing you the longitude time sections of the sea surface temperature anomalies in color shading and surface wind anomalies in vectors along the equator for Indian Ocean, Pacific Ocean, and Atlantic Ocean for the 1-year and 2-year La Nina, as well as their difference. The stronger preceding El Nino before 2-year La Nina will trigger stronger initial warming over the Indian and Atlantic Ocean, as well as a stronger cooling in the tropical Pacific. So the initial warming of the Indian and Atlantic Ocean will delay the adjustment of the other 2 ocean basins to the cooling in the tropical Pacific. As a result, after the mature phase of the first La Nina peak, we can see the warmer SST over the Indian and Atlantic Ocean, as well as the stronger La Nina amplitude, will make the easterly wind anomalies more persistent over the western equatorial Pacific in 2-year La Nina and prolong the duration of event. The existence of these long-lead precursors indicate the predictability of the La Nina duration, but the current operational ENSO forecasts are limited to 1 year, which is not sufficiently long enough to explore the predictability of multi-year ENSO events. So we conducted 2-year forecasts with the CESM1 simulation. We first make use of the decadal forecasts, which are initialized on November 1st of each year during 1954 to 2015. For each initialization, there are 40 members initialized from the same oceanic and sea ice states close to the observations. And ensemble spread among the 40 members is generated by adding small perturbations to the atmospheric initial conditions. And for decadal forecasts, they are run forward for 10 years for each initialization. We also conducted 2 additional sets initialized in March and June to explore the seasonal dependence of ENSO predictability and prediction scale. And we interpret the ensemble mean signal of individual members as the predictable component of ENSO, which mostly arises from the oceanic initial conditions while the ensemble spread is estimated by the individual spread among individual members, which is associated with the initial atmospheric noises. Here I'm showing you the forecasts composited for the 1 year and 2 year La Nina events during this forecast period. The black curve shows the observations and the colored curves shows the ensemble forecasts with 6 different lead times relative to the 2nd December. By doing so, we can explore what is the maximum lead time by which we can predict the duration of La Nina. For the 1 year La Nina, its termination is first captured by the forecasts initialized in June, near the onset of the 1st year La Nina, while the November initialized forecasts shows improvement in predicting the amplitude in the 2nd December. For 2 year La Nina, its development and continuation is well captured in all 6 different ensemble forecasts with lead time up to 25 months. On the right, I'm showing you the distributions of the predicted Niño 3.4 index in December +1, so that's the 2nd year. And we can see the frequency distributions for the 2nd peak of La Nina is similar across all the different lead times, which indicates there is a high predictability of the 2 year La Nina events. Then we'd like to explore what are the mechanisms behind the predictability of La Nina event duration. So I'm showing you the sea surface temperature anomalies in color shading, thermocline depth anomalies in black contours, and surface wind anomalies along the equatorial Pacific for both 1 year and 2 year La Nina events, and for observations and the forecasts initialized in November near the 1st year La Nina peak. We can see the November initialized forecasts have different initial conditions. There is a positive thermocline depth anomalies for the 1 year La Nina in the Western Equatorial Pacific indicated by the solid contours, while it's negative for the 2 year La Nina events. And also the initial thermocline depth anomalies are more negative across the Equatorial Pacific. So when the forecasts are initialized from such distinct initial conditions, they show different evolutions in the subsequent seasons. The thermocline shoaling in the peak of 1st year La Nina is related to the preceding strong El Nino. So when the forecast is initialized from the peak of the strong El Nino, they can also well capture the evolutions of thermocline depth and SST anomalies for the 2 year La Nina events. The dynamics and predictabilities for 2 year La Nina following strong El Nino is well understood, but not all of the 2 year La Nina follows strong El Nino, as also mentioned in Mike's talk. So here I further classify the 2 year La Nina into those following strong and moderate El Nino. We can find for the 2 year La Nina following moderate El Nino, when the forecasts are initialized from the peak of moderate El Nino, they do not well capture the development of the 1st year La Nina and also underestimate the amplitude of 2nd peak. While the forecasts initialized with the later date show improvements, so it indicates that there are factors external to the preceding El Nino that can affect the predictability of multi-year La Nina events. And recent studies have explored the influences from Indian, Atlantic, and North Pacific Ocean in affecting the multi-year La Nina events. And the relative importance of the ocean basins needs to be isolated, maybe using the sensitivity prediction experiments. In the rest of the talk, I will show some preliminary analysis for triple La Nina events. Here, I further classify the 2-year or longer La Nina events into those lasted exactly 2 years and 3 years. In the historical record, we have 6 triple La Nina since 1900. In the composite comparisons, because we only have a few samples, so the results are not very statistically significant, but on average, triple La Nina is even preceded by a stronger El Nino. But when we looked into the individual events, like 3 of them are following moderate or even negative states. And in the CESM1 pre-industrial control simulation, we identified 58 triple-year La Nina, which accounts for about 16% of the total La Nina events. And again, in the composite comparisons, triple La Nina is preceded by stronger previous El Nino, but the individual events have a wide range of precursoring conditions. So there are more analysis are needed to understand the dynamics controlling the duration of La Nina events, and especially triple La Nina. And here I'm going to show you the CESM2 multi-year forecasts for the triple La Nina in the current state. And NCAR has recently released a new suite of seasonal to multi-year prediction system conducted with CESM2. It has 4 initialization, including November, February, May, and August for each year during 1970 to 2020. And for each initialization, there are 20-member predictions and have been integrated for 2 years. And here I'm showing you the ensemble mean forecasts at different lead times for the current weak triple La Nina state. Some of the initialized forecasts can capture the second peak, but none of them predict the third dip in the upcoming winter. And here I'm showing the individual members. So the left 2 are the 10 members from the November initialized decadal forecasts. We can see the forecasts initialized from the peak of the preceding week El Nino. The ensemble mean tends to capture the first and second peak, but there is a large spread among individual members, while the forecasts initialized near the first peak of La Nina, it fails to capture the second year peak. And the latest initialization is in May of 2021. It captures the second dip, but fails to capture the upcoming dip. So if we have most recent initialization with even shorter lead time, that might be better prediction for this current state. In contrast, here I'm showing you triple La Nina events following strong El Nino in 1997. And on the left, I'm showing you the ensemble mean forecasts with different lead times. You can see these forecasts very well capture the evolution of this triple La Nina. And on the right, I'm showing you the 10 members of the decadal forecasts, which has longest lead time. And in CESM2, the 10 members can capture the first and second dip when they are initialized from the peak of strong El Nino. And I also put the results from CESM1 here. It also shows very similar results. And with the 40-member decadal forecasts, we can see that when the model is initialized from the preceding El Nino, it will very well capture the evolution of this triple La Nina. So that indicates that the strong El Nino and associated discharge processes is useful predictor for the triple La Nina. In the last two slides, I'd like to show some statistics, and you may wonder how frequent are those extremely long events. So here I'm showing you the distribution of number of triple La Nina events over any 100-year segments from the CESM1 control simulation. And we can see most of the segments tends to simulate 3 to 4 triple La Nina per century. And this is from the results based on a 2000-year control simulation of CESM2, and CESM2 tends to simulate 1 to 2 triple La Nina events per 100 years. And I'm also looking to the projections of frequency of triple La Nina using the CESM1 and 2 large ensembles. For CESM1, there are 40 members running under the CIMIC 5 radiative forcing during 1920 to the end of, thanks, sorry, just one more slide. The end of the 21st century, and here I'm dividing them into two 90-year period, and we find that in CESM1 projects a higher frequency of triple La Nina in the future. However, in CESM2 large ensemble, there is a lower frequency in the future relative to the historical time. So more analysis is required to understand the differences in different model projections about triple La Nina. In summary, we find that about half of the La Nina events lasted 2 years or longer, which will cause long-lasting climate impacts. We find that the leading factor for La Nina duration is amplitude of preceding El Nino, which modulates equatorial Pacific thermocline shoaling and interbasing atmospheric adjustments. Other factors may also play a role, including the variability in other ocean basins that are external to the preceding El Nino and El Nino precursor. The duration of La Nina events is predictable with over a 1-year lead. Multi-year La Nina following strong El Nino is highly predictable with 2 to 3 year lead time. Long control and large ensembles of multimodal simulations are required to constrain the statistics, dynamics, and projections of the triple-year La Nina events. That's it. Thank you for your time.
Okay, thanks, Xian. It's really excellent talk, and which I think nicely compensated the previous ones. So we're now taking questions for the 3 speakers. Note that although some questions will be directed to one speaker, all the others are free to aid and something you want. So to me, the first, I think several of audience are asking about the name of the triple La Nina events. So for example, Andrew said maybe we should call it double dip La Nina or triple year La Nina, this kind of question. So Mike and Fei and Xian, can you answer? What do you think the name, proper name for this La Nina events? Any ideas?
Yeah, I kind of favor double dip and triple dip because it's snappy, and you know, it conjures up image of ice cream cones. You know, it's something that makes you feel good. So I mean, we can I mean, the name is, I'm not sure it's that critical, but you know, it's 2-year, 3-year La Niñas. You know, it's, but I do like double dip, triple dip because it's snappy and it captures attention.
So what do you think, Fei?
Okay, I think whatever. Any level is okay because I think people should more focus on its influence of this kind of La Nina, not just its name. I think this one is more important.
Great. Marcus?
Yeah, so we can go to the next question. So there's a large number of questions, and if you have more questions, just put them in the Q&A box, and we try to get as many done as we can. There's 2 questions, and I think they mainly relate to Mike's talk, but maybe others also have a view on this, which are by Antonietta Caprondi and Matt Collins, asking for the conditions in the Indian and Atlantic, and if these support continuing La Nina is one question, and the other is, can you say anything about the longer-term outlook of the IPO? Do extended La Nina events precede positive, negative IPO events?
Yeah, so about the IPO, I mean, there is a chicken and an egg issue here. It's what causes what. You know, often, I mean, sort of the null hypothesis for the IPO is it's just the residual of periods where you have more or fewer El Niños or La Niñas, and that determines the amplitude and the phase of the IPO. So, I mean, you could argue that this 3-year extended period is the beginning of a negative phase of the IPO, because this is really the long-term average is going to show up as an IPO-like structure. You know, if there are intrinsic dynamics to the decadal time scale that are independent of ENSO, then that's making it easier for it to be cold in the equatorial Pacific in a negative phase of the IPO. But I think this is, you know, this is really a fundamental question: is what's causing what with regard to tropical Pacific decadal variability? Is it independent of ENSO and has its own intrinsic dynamics, or is it just a reflection of you know, random fluctuations in the variability of the ENSO cycle? So what the other question was?
The other was about the current conditions in the Indian and Atlantic Oceans, and if they're supporting a continuing La Nina.
That's a good question. I haven't looked closely at the current conditions in the Indian and Atlantic Oceans, and so I'm sorry I didn't do my homework on that one. Maybe others could answer that question.
Yes, anything. Fei and Xian, would you like to add something?
I just checked the ENSO predictions from NOAA CPC, and there is like about like 0.5 to 1 degree warming over the tropical Indian Ocean. Oh, sorry, tropical Atlantic Ocean. And I remember there is a like warming in both Indian and Atlantic Ocean earlier this year. So that might favor the development of the 3rd year La Nina.
So is there any continual warming in over the Atlantic, tropical Atlantic Ocean? Or the current stage of the Atlantic Ocean is still warming, or?
It's warming.
Okay, maybe influence the next year, the continual La Nina for next year.
Yeah, we are not like, we don't have the confidence to say that.
Okay.
So I have a question for Xian on that topic.
Yes.
In your model simulations, did you see any 4-year La Niñas?
Oh.
I didn't check that. In the 1800-year simulations, we have 58 triple La Nina. I didn't further looked into the fourth, I don't know, but it's lower frequency. Should be very low frequency.
Okay, there is
Yeah.
also a question about the 4-year La Nina events in the paleoclimate record. So anyone, do you know the paleoclimate records have any 4-year La Nina events?
It's never happened, occurred for the La Nina, 4-year La Nina event since the historic record, right? So I don't know whether we have some.
Anyways, it's an interesting question. We have 3 years. We might have 4 years in the future, if possible.
Yeah.
Okay. So another question is about the subseasonal events. So, you know, MGO and the BSISO, this kind of subseasonal variability, how does subseasonal variability impact the ENSO and also triple La Nina events? Any perspectives?
Yeah, I think there is a stochastic element to the wind forcing, that's for sure, and it doesn't necessarily. It's not an either or thing with regard to, say, interbasin interactions, because the large scale conditions may be set by forcing from outside the Pacific Basin, but the changes in the wind field will have not only that direct forcing structure to it, but also there'll always be a random component. So I don't think it's necessarily either or, and I would expect that if we looked in more detail at the wind variability over these past few years, we'd see a lot of trade wind surges that are part of the structure of the wind field associated with this La Nina.
There's a couple of questions also, and I guess this is also quite expected in the context of global warming, asking, for example, how the increase of temperature in the oceans due to climate change is influencing the experience of La Nina and El Nino, and the accuracy of the prediction models. And there's another particular question also, if the trend of warming in global oceans could be promoting for more triple La Nina events. Who wants to take this?
I can.
Those are great questions. Oh, okay.
Yeah, I think it's still open question. From my preliminary analysis using the multimodal large ensembles, I also looked into other models in addition to CESM models. And we find that, first of all, not all of the models can well simulate the characteristics of La Nina evolution. Some models don't even simulate multi-year La Nina events. And also there is a large spread in the projection of the La Nina duration as well as the frequency of triple La Nina among models. So it requires further examination.
Mike?
Yeah, there is a warming trend in the Western Pacific warm pool region, and it's not only the sea surface temperatures, but the upper ocean heat content is trending up. And in fact, the latest values of heat content in the Western Pacific warm pool are the highest in at least going back to 1980. So there is this trend, and I think this may be affecting that relationship between upper ocean heat content and sea surface temperature. That is sort of the cornerstone of Fei-Fei Zhen's recharge oscillator theory. And it may be that, if you filter out that trend, something more like pure recharge oscillator dynamics might emerge. But, certainly there is a climate change signal in there, at least if part of that, if that trend is largely due to climate change, and it probably is. So, so at minimum, it's affecting our diagnostics. Now, it may also be affecting the dynamics as well. And that's a really, I mean, this is in fact, one of the most urgent questions in Earth system science is this relationship between ENSO and climate change, how it's affecting variability today and how it will affect it in the future. And so this is a wide open area for research, and I hope people really pursue this problem because it is so important.
Okay, thanks. So another question from Bob is, could the neutral to negative Pacific meridional mode in the last 3 boring springs have influenced the development of the double dip or most like triple dip La Nina events? So Mike, can you try to?
Yes, I think the meridional modes may have a role to play here. In our study, we did not consider those. We focused mostly on the interbasin interactions, but our second speaker, Fei Zhang, talked about off-equatorial influences from the South Pacific, and I think that is a viable mechanism. I think what we need to do, I saw another question in the chat, how do you prove one or the other? And I think we need more experimentation. I mean, you can never really prove anything, 100%, but I think what we need to do is we need to do the model studies, the kind of controlled model studies to look at these different mechanisms and try to quantify their relative influences. So I think that's kind of the next step. I think the first step is just trying to make sense of what the observations are telling us, and then from that formulate hypotheses that are testable in a model context, and also looking at historical data to the extent possible, and paleo data.
Right. Fei, do you have anything to add?
Yeah, and we just evaluated based on the signal prediction scales to check whether, especially from the spring season, because when we started from the spring season, we also failed to predict the following evolution of ENSO sometimes, and now we find some useful information, even which are more convenient for to judge the following evolution rather than the subsurface temperature structure, just from the surface wind, and especially after 2000, I think is more useful for that. But whether there are some decadal shift or decadal change of this event background, I don't know. Maybe we need to check more for this to make more useful prediction. Yeah.
So thank you. There are a few questions actually also about remote effects and teleconnections of La Nina events in particular, for example, regarding the current drought in East Africa. But maybe synthesizing these questions and rephrasing them a bit, in the context of a triple or double La Nina, are you aware, for example, that certain teleconnection patterns maybe turn out more robustly in this kind of prolonged events compared to shorter La Nina events?
Yeah, that's a good question, whether the duration of the event is affecting the strength of the teleconnection. I'm not clear about that, but certainly the changing background conditions due to global warming are affecting the intensity of the events. I mean, Australian rainfall is a good example of that, where because of global warming, the waters are warmer around Australia than they have been in the past. And then you have a La Nina event that warms the Western Pacific even more. And so, the nonlinearity of the Clausius-Clapeyron relation tells you the atmosphere can hold more moisture. And so the normal rains that you would expect from La Nina become extraordinary rains because of this combined effect of La Nina warming in the far Western Pacific on a global warming trend. So I think the impacts of ENSO are being amplified by the changing background conditions, which is a different issue than whether the dynamics are being affected. I mean, even if climate change has had no impact on ENSO and it's just the same up and down, variation that we see, the fact that those ups and downs are occurring on a warmer background is producing impacts that are amplified in many situations. But the duration of, I don't know about how the duration of the cold event would be affected, other than the fact that you're going to see multiple years of the same kind of disasters like we're seeing in Australia, and the extended drought that's gripped the western half of the United States. I mean, there's an underlying warming and drying trend from climate change, but the extremity of the past couple of years is the direct effect of La Nina impact. And so it's the duration of the impacts because of these multi-year events that's really beginning to affect parts of the world in serious ways.
Okay, so there's one specific question to Xian, actually. So from time, with the triple La Nina events, can we expect a repeat of El Nino in the coming years?
And I think for the current state, we don't have a strong subsurface precursor. So this current condition might be more influenced by some stochastic processes and influences from other ocean basins. So we cannot make a sure prediction about the next year.
We might have.
Yeah, actually, our model has predicted that should be a El Nino event in the next year, but it has a very large uncertainty for the prediction results. But I think, but I don't know whether we will meet a 4-year La Nina event or change to El Nino event. We don't know, but maybe get closer, we can get a robust prediction results. Okay.
Mike, anything from NOAA? Any predictions from NOAA?
I think the assessment that NOAA came out with on November 10th, about 2 weeks ago, was basically for cold conditions to dissipate by the boreal spring. And then, we're going through the spring predictability barrier at that point. And so it's really kind of a crapshoot as to what might happen, in the following year. I'd like for somebody to come out and make a really strong prediction for a major El Nino, so we'll have more to shoot at when it doesn't happen. But I don't think NOAA's not going out on a limb much past the the boreal spring.
We probably have time for maybe two more questions. There's a specific one, or for Mike, Mingyu Park saying, "I'm sorry if I've missed this part, but what was the cause of the 2021 Atlantic Niño? From the schematic, his impression was that the first year cooling affected this Atlantic Niño. Then does the second year cooling also impact similarly?"
That's a good question. I mean, in my presentation, I focused on the impacts from outside the Pacific Basin on the Pacific Basin, but it goes the other way too. In fact, there is a tendency for cold Pacific conditions to force warm Atlantic Niños, but the relationship's a bit inconsistent. It doesn't happen all the time. But it's a reasonable hypothesis that the first year La Nina in the Pacific, the first dip of that La Nina, forced the warm event in the Atlantic the following summer, which then would have potentially fed back to the Pacific again to reinforce the cold. So that's an interesting scenario, and it's one that again would be interesting to test in the framework of controlled model experiments. But it's plausible.
Okay, thank you. Yeah, I think we have to wrap it up now. We are at the end of our 90 minutes. This was 3 really excellent presentations and really providing very nice perspectives on this ongoing triple year Vanilla event. Let's give a round of applause to thank our speakers and thank you. Yeah, for these excellent presentations and also for answering these questions. And also thank you to all of you who are online and were posing questions today. Again, we intend to have these webinars roughly every 2 months, which means we are planning the next webinar of the series for the end of January and are currently finalizing discussions about the next topic. Okay, thank you for this very nice.
Okay. One final words to add that because someone asking when they can access the video, the record, so it will be available in a couple of days. So it will be very soon. Thanks.
Thank you. Great session.
Thanks. Thanks,
Thank
Mike.
Thank
Thanks,
you all.
Dave.
Thank you. Thank you very much.